have charge and discharge on the supercapacitor, and in those cases, those are linear charge and discharge curves. That's not ideal from a electrical engineering standpoint, engineering a load to work with that power source, whereas the rechargeable battery is much flatter in its voltage profile as discharge happens. I want to say a few words about the packaging of batteries and supercapacitors, and I'll start with this. We all, I think, in this room, and probably most of the people watching, care most about the active materials in batteries and supercapacitors, or if you're working on fuel cells, the active material, the thing that makes it work fundamentally, right? Or solar cells. But there's another part of any of these devices, which is how to put them all together, put the active materials together with the electrical leads that need to take in the power, send out the power, and the materials that go around the devices to protect them from harm and to protect you, the user, from harm. Many times we have chemicals that are toxic inside of these devices, these energy storage devices, and we don't want them getting out. They will hurt people, right? In some cases, they will cause catastrophic failures, right? So you probably saw the Boeing Dreamliner. When it came out in the first month, it was catching on fire, right? Spontaneously. That was really bad. You know, billions of dollars had been spent to develop that airplane over many, many, many years. And in its first month in practice, in the field, right, it was catching on fire. And what was happening there? It was a lithium-ion battery problem, okay? So that's a serious issue, right, of trying to make sure that our energy storage devices are safe. It's crucial. It's fortunate that all of those episodes happened when the plane was on the ground, not in the air. Now, so here's some factors, some principles of good package design. I think that many of you, if you work on energy materials and you do a good job, you will have to think about the packaging part of the problem. Because what it means is that you were successful in making a primary, an active material, and somebody said, I want you to go the next step and take it to a more functional form, right? So that means you were successful. If you are unsuccessful in the active material part, you won't have to worry about packaging it because no one will want it, right? It can stay in your laboratory and it will never be exposed to the outside world. So I think you should want to learn about packaging, because even if you're working on active materials, because it will be a sign of success if you end up working on this subject later. So how do we package supercapacitors and batteries? Well, there's a few main ways to do it. They're listed here. I showed a picture of this, the cylindrical form. This is the one that's the most common, familiar to us. The cylindrical package, where we take a roll, sometimes we call that the jelly roll, of electrodes, electrolyte separators. We do it similarly for batteries and supercapacitors. And then we put it into a metal sleeve. We connect it to contacts on the top and bottom, and that's our device. The one on the top right is a prismatic form of that cylindrical package. It has some advantages in the sense that that it can be packed together more densely than the cylindrical form factor, but it also has some other issues with regard to cooling. It's harder to cool because it actually fills the space more than a cylinder does. If you close pack cylinders together, you have some voids between them that you can use to cool the devices, whereas the prismatic packages don't have as much of that open space. A pouch package on the bottom right, this is one that's somewhat flexible. You leave a little bit of extra room inside. It may be vacuum at first. Okay, you might vacuum package, and so the pouch actually seals over conformally to your stack of electrodes. But over time, there'll be some side reactions in batteries mainly, but also can happen in supercapacitors that release gas, right? And that gas can then fill the pouch a little bit. And we'll talk about that some more. And then the bottom left is button package. This is actually really, these button batteries are very useful for doing laboratory experiments with, because they're easy. You can buy a little crimping machine. They're inexpensive. You use these with stainless steel components, and you can do quick tests without having to build a big packaging enterprise in order to test your ideas. So the cylindrical, I'm going to go through advantages and disadvantages. The cylindrical packages tend to be really tightly sealed. There's a lot of good crimping technology. Part of it comes from the food packaging industry, canned foods, for example. And so that it has good calendar life. It's economic. But it tends to be heavy because there's a lot of package relative to the active material. And it has a relatively low packing density because of that, because of those cavities between the close packed batteries. So the markets, you know what they are because you use these all the time. AA, AAA batteries. Prismatic packages are more common for your cell phones, right? And things that are low profile. You'll slide those in. You'll slide in and make contacts. And in fact, in some cases, the prismatic package is made very, very, very flat, right? And in doing so, you could put it into ultra thin things like laptops, thin laptops, and so forth. They're generally more expensive to make. They're a little bit less good at doing heat transfer, although I think that that can be overcome. They tend to have a shorter cycle life, and they if they have a really thin wall, then they're susceptible to damage. It's sort of like an arch is a more structurally sound thing than a plane. And so the package is planar, it's easier to dent, for example. So the markets are listed here. Prismatic packages, excuse me, are starting to make some inroads into things outside of the consumer electronics or portable electronics, into electric vehicles in particular. Pouch packages are here. Just a real quick look at these. The advantages are that they're flexible. So when you hear about wearable electronics, I'm sure you've heard about it, right? You would imagine that the power source for wearable electronics will probably be in a pouch type format. And they can be lighter weight because you can have instead of having a hard metal enclosure, you can take a polymer, you can metallize that if you need to have a metallic finish to it, but it remains flexible. The problem is that the sealing isn't as good, usually because it's there's just thinner things and polymers instead of metals, and typically these would be custom designed for a particular product. So you don't see the pouch batteries in your everyday life as much. A lot of times they're hidden inside of something else that you're using. Okay, so for example, the laptop that I'm using, an Apple MacBook, has a pouch-like battery that's custom made for this particular product. And then lastly, button packages. I mentioned before, they're useful mainly because they're so easy to make and you can test. So I like them more for research use than I do for real world use, where they're used in watches and pacemakers, some biomedical things. But they're usually not rechargeable. They're hard to charge quickly. They're not good at taking a lot of current, but they're great for testing your design. So if you're working in batteries in research right now, you should have a capability of doing button battery manufacturing and crimping and all that. Ritu, do you have that in your place? Yeah. So you can use Ritu's. Do you have a decrimper? She has a decrimper too, so that's good. And you can take it. Oh, we're going to have a demonstration about this very thing. Yeah, good. All right, so here's a high-level summary of what we just talked about, and then we'll move on toward the wrap-up. We're about halfway through right now. You have the cylindrical is by far the most common, but it's heavy. It has low packing density, so it's heavy on its own, and it's also heavy if you have to integrate over the total space, the total volume that it occupies. At the same time, it's still popular even with automotive manufacturers because you do have these voids that you can use to cool the devices, and it turns out that from a marketing standpoint, one of the difficulties in selling electric vehicles has been the long time it takes to charge a car, a purely electric vehicle. And a lot of that has to do with the heating that would come with ultra-fast charging. And so having that little extra space is actually, can be good, because what you'll do is you'll actively cool your battery while you're doing very fast charge. So the automotive companies now, I think, are trying to get almost full charge in 1 hour. Right, so that, for example, you could go to work and in the morning on partial charge, and then you realize, well, I'm not going to be able to go home until, unless I can charge my car, but you can just go to lunch and charge your car during lunch at some public charging station, and you would be able to fully charge your car and get back home. All right, so I'm going to focus the rest of the talk on the supercapacitor market. Most of what we talked about here was really primarily relating to batteries. So this is based on a talk that was given by Bob Hamlin, who's a person in the U.S. Research community. Spent a long time with the Army Research Office on doing battery work with them. And so he's got a lot of useful insights. The first thing I'll show you is a Ragon plot. You're going to see these more and more throughout the week. Again, Ragon plots, they list power density as a function of energy density, or vice versa. It depends on, I guess, your preference or what you're focusing on. But it's important to understand that batteries have high energy density but low power density, and pure capacitors have high power density but low energy density. And supercapacitors are these things that are supposed to bridge the gap, okay, between the two. I'm not so sure that that this curve is showing everything. I don't know exactly where the numbers come from. Obviously, what you would want more than anything would be to go to the top right of this graph, where you have both really high power and high energy density. Right, that would be ideal. For reference, fuel cells are also listed here. They're very much like batteries, except they have even higher energy density, right? And that's why fuel cells are, at least contemplated and now, close to hitting market for automobiles, because energy for the automotive market is the most important thing, or has been the most important attribute for an electric vehicle or a fuel cell vehicle, because of the range, right? The world is completely accustomed to a tank of gas in their vehicle, allowing them to go 300 or more miles. Right? That's what's happened in the marketplace. And so anything that falls short of that is downgraded, is less attractive to consumers, and that's why this energy density is so important for that market, for electric vehicles. So I'm just going to go through a few things here, talking about the different types of capacitors. Again, mostly this is for your benefit in nomenclature, so that you understand the lingo and what things are called. So we have, if we just say that an electrode is capacitive, that would mean that it would be more like a traditional electrostatic capacitor, in which case you could have a metal with a dielectric on it and another metal on the other side, and you're storing your charge in your dielectric and in your layer of metal. Electric double layer capacitors, I talked about a little bit. We'll talk much more about it. Those are ones in which the charge in the electrolyte forms, and there's a high surface area usually, and you use that surface area to enhance your capacitance. And then we have the last type, surface Faradaic reactions. So this is where you're enhancing the double layer effect with some fast redox reactions. Okay? And those can take a number of